Okay, found an ancient Chinese proverb that says, if you are not part of the solution, you are part of the precipitate. So some terminology that we need to get out of the way first. A liquid is a substance with a definite volume, but no definite shape. It will take the shape of its container, and that's what makes it a liquid. A gas is a substance with no definite volume or definite shape. It'll not only take the shape of a container, it will fill a container completely. And that has to do with the movement of the atoms. In the liquid, they're very low energy and they're confined more. In the gas, higher energy and spread out. In a solid, you have a substance that has both a definite volume and a definite shape. And that's because the atoms are at their lowest energies and stay within the container and keep their shape. You don't take the shape of the container. A solvent is something that dissolves something. Words we're used to. Maybe not so well known by many. Solute. The solute is that which gets dissolved in order to make a solution. And a solution is a combination of that solute and the solvent. And how do you know which is which? Well, what we normally say is whichever one there's more of, that's the solvent. And the solute is the one that there's less of. We lose the PowerPoint. Okay. A precipitate, which was mentioned in that ancient Chinese proverb, is the part that is not dissolved. So when the solution, say a liquid with a solid put into it, as the solid dissolves, it'll get to a point where it can't take anymore, where it's called saturated. And then what doesn't dissolve is called the precipitate. It can also be a condition of you are mixing some liquids or solutions, and you have a reaction, and the reaction forms something that won't dissolve in whatever solution you're using, and so it becomes a precipitate. A solution has one substance dissolved in another. It is not a process of melting. The salt doesn't melt in the water when you add it to it, sodium chloride. It's also not a chemical reaction between substances. It's a physical process. Dissolving is a physical process, not a chemical reaction. It's also not a change in phase. It is not a solid becoming a liquid. The definition of a solution says that it is homogeneous. That means it's the same throughout. You go to any one place and it's all the same. If you have sugar dissolved in your tea, if it's dissolved in it, so you have a solution, then you take a sip of that tea from anywhere in the glass, it's going to have the same amount of sweetness. And that's a real good thing, because if you have air is homogeneous. It has all these different gases in it. That's very convenient, because we don't have to get up every 5 minutes and go lay down on the floor over there and take a breath of oxygen. No, the oxygen is everywhere. It's all spread out. If it were not homogeneous, we call that heterogeneous, and that means you have a mixture. One example of that is concrete. Concrete is a mixture of cement and gravel. In a solution, you cannot see what was dissolved. It becomes invisible. It is part of the solution now. Also, if you shine a light through a solution, the light beam does not scatter. It goes straight through. If it does scatter, then you have what's called a colloid. Example of that I gave there is fog. If you shine a light in the fog, then the light gets scattered everywhere. And that's why you don't want to put your high beams on in the car if you've got fog, because it'll end up shooting right back into your eyes and blind you, make it harder to see. And there's a lot of colloids. Smoke in the air is a colloid. I used to demonstrate this by burning some paper in a Erlenmeyer flask and then shine a flashlight through it. And you see that the light scatters because of the smoke. Milk is a colloid. It is homogenized, but it is not, it is completely homogeneous, but it does scatter light. So milk is actually a colloid. Solutions are stable. They can't be filtered. A while back we were talking, I said, if you had a mixture of sand and salt and water, how would you separate it? And somebody said that they would start by filtering out the sand. You can do that because it's a mixture. If the salt's dissolved in the water, you can't filter the salt out. You'd have to do something like boiling the water in order to make it leach salt. And then you can always reclaim the water. So some examples of solutions with our different phases. So air is a solution. For example, you have oxygen dissolved in nitrogen. Why is it that way? Because there's less oxygen than there is nitrogen. It's about 20% oxygen and almost 80% nitrogen. And that's a case of a gas dissolved in another gas. Now the next one there would be a liquid dissolved in a gas, and I can't find any. And I've looked a lot. You will find ones that say water dissolved in air. Well, if it's liquid water, then it's not dissolved in the air. And if it's gas vapor, that's a gas. If water vapor is a gas. And so it's not a liquid dissolved in the gas. Same goes for solid in gas. I've found a few things that have said, I won't remember what, hydrogen sulfide in, it wasn't paraffin, it was naphthalene. No, that's not a good example of that. It's not an example of that at all. No. So, a gas dissolved in a liquid. That would be a good example. Carbon dioxide dissolved in water. And that, for instance, Dr. Pepper. And we're going to look later at what things affect that gas being dissolved in the water. An example of a liquid dissolved in a liquid is rubbing alcohol, which is made up of isopropanol and water. And if you take 50 milliliters of water and add 50 milliliters of alcohol, your final solution will be 98 milliliters. And that's because the alcohol will actually dissolve in the water. Salt water is an example of a solid being dissolved in a liquid. The salt is sodium chloride and it's dissolved in water. A gas dissolved in a solid, a really good example, is hydrogen dissolved in palladium. And that's what happens with palladium-hydrogen electrodes. Dental amalgam is an example of a liquid being dissolved in a solid, And normal amalgam was mercury being dissolved in gold. Nowadays, a lot of people are using different amalgams. They're worried about the mercury. But be aware, if you have mercury fillings, taking them out will release more mercury than what leaving them in would do during your lifetime. So it's a really bad idea to remove them. It's also expensive to do that, remove and replace. And one more, if I have the table back. What we call alloys are solids dissolved in solids. So brass is a case where zinc is dissolved in the copper. So what factors affect the rate of solution? Now this is not how much will dissolve, it's saying how fast it will dissolve. Temperature is a very important one. Stirring is another factor for how fast things dissolve. The size of the particles that are dissolving is important, and so is the amount of solute. So let's look at each one of these. Temperature, for example. The higher the temperature of the solvent, remember that's the substance that does the dissolving, the faster those solvent molecules are moving. And so they're going to dissolve faster. That movement increases the number of collisions between the solvent and the solute. And so that the solute, which is getting dissolved, dissolves faster because it's coming in contact with the solvent more frequently. But it's the opposite effect if you have a gas. With a gas, you dissolve faster if you have the solvent at a lower temperature. So when making Coca-Cola, they'll have the liquid cold in order to dissolve the gas faster, and later we'll see also to dissolve more. Stirring is another factor that affects how fast. It increases the frequency of those collisions again between your solvent and your solute. So the stirring makes it dissolve faster. Go ahead and stir the sugar in your tea, it's going to dissolve faster than if you just let it lay on the bottom. Particle size also affects how fast. The smaller the solute molecules are, the greater the surface area to volume ratio, and that will let them dissolve faster. That difference means that a very large percentage of the solute gets exposed to the solvent, and it's when they're exposed that they get dissolved. And then lastly, the amount of solute. So a low solute to solvent ratio, meaning very little of the solute, and a very high amount of solvent, that will increase the rate of solubility. It will dissolve faster. Because there are more solvent molecules to dissolve each of the solute molecules. Now, solubility is defined as the maximum quantity of the solute that can dissolve in a certain quantity of a solvent at a specified temperature, because remember we said temperature changes things. So what are the factors that affect the solubility? How much will dissolve? Not how fast, not the rate, but how much, the quantity. The nature of the solute and the solvent. Well, what do I mean by nature? That means the polarity of the molecules. Temperature will affect it also. Generally, if you have an increase in temperature, then you have an increase of solubility. The solids will dissolve faster in a hotter liquid. but it's the opposite for a gas. And you cannot dissolve as much gas in a warmer liquid. That's why if you're going to make a Coca-Cola cake, you first heat up the Coca-Cola and make the carbon dioxide leave. Pressure can also affect it. So your Coca-Cola comes in sealed cans, and when you open that can, you hear a release of pressure. That higher pressure was maintaining more carbon dioxide being dissolved in it. For solid and liquid solutes, the change in pressure will have basically no effect. It doesn't do anything. But when we talk about gases, that increase in pressure can make a big, very big difference. So some terms that are commonly used when talking about solubility, and you'll see this in tables and references. They'll use the letter S for soluble, and can we have that back, please? When a solid completely dissolves in a liquid, then it's soluble, if it will dissolve. But if it only dissolves a little bit, then that's called slightly soluble, or SS. And insoluble, or IS, is when it won't dissolve at all in the liquid. Immiscible is when one liquid doesn't mix with another and forms layers. Here I have a lava lamp. Unfortunately, it's still cold because it started out in my garage. And but it's got a light underneath, and as it warms up, there's a layer of paraffin in there that will expand, and it will rise up and float, because remember, lower density will float on top of higher density. Then as it moves up, it gets cooler, and then it contracts and sinks back down. And so you get the flow of the essentially candle wax inside, moving up and down. And that's how a lava lamp works. And when they're immiscible, you can form layers. So you may have seen a gradient where you had different liquids like water and oil, mercury. The mercury goes to the bottom because it's the densest, then the water, and the oil is the least dense, so it floats on top. That's why when you get your first rain, it can be dangerous driving, because there will be a very thin layer of oil on top of the water from cars having driven in the past. And so that oil's on top, it lowers your friction and end up causing accidents. Miscible is the opposite of that. It is when a liquid completely mixes with another liquid. And alcohol and water is a good example of that. Solubility curves. Now these are curves for individual elements, and each curve has a label as to what compound is involved in it. So this one over here is for sodium nitrate. It's that curve there. So the x-axis here is temperature in degrees Celsius, and the y-axis is how much will dissolve. The graph shows that red square there. At 10 degrees Celsius, 80 grams of sodium nitrate will dissolve in 100 grams of water. You do have to specify the volume of the liquid here. So you could, if you needed to know how much you could dissolve at 10 degrees Celsius, you look on that chart and you find 50 grams that you originally had would not dissolve in that. Only 40 grams of the sodium nitrate would dissolve, and you'd be left with 10 grams looking like a precipitate. To explain what I'm going to go over later, we need to cover this. This is a vocabulary concept map that I made for the mole. The mole is a really important concept in chemistry and in biology. And we begin with what is the mole? The mole is a number that means 6.02 times 10 to the 23rd particles of a substance. It's always that number, 6.02 times 10 to the 23rd. It is a number. What's it like? It's like saying a dozen. Your mom could send you to the store for a dozen donuts. That's 12. She could send you to the store for a mole of donuts. That would be 6.02 times 10 to the 23rd. That might take you a while to bring home. Another number is a gross. A gross is a dozen, or 144. Paper comes in reams. You open up a package of paper for the copier or your printer, and that's 500 sheets. One ream is 500. Some other examples of moles that are not what we're talking about is the animal, the mole, and with a face that only a mother could love. That one's the star-nosed mole, my favorite. They're not found around here. They're basically in the northeastern United States, and they're much larger than the moles we find here. Ones here are very small. Here we have a mole on skin. You may have heard of the ABCD rule. That's for determining if a mole is a melanoma. If it has an irregular border, it's asymmetrical, it has different colors, and had diameter greater than 5 millimeters. So that mole meets all of those. That is definitely a carcinoma. And skin carcinoma is one of the worst things you can have. The breakwaters are moles. Sometimes people will just put broken up concrete on the coast sticking out to keep the water, the waves from destroying the beach. Then we have the mole who's an undercover spy that you'll never know what they are until they're activated. And then my favorite here is chicken mole. That's a chocolate sauce on chicken. It's a Mexican dish that's quite delicious. Some examples of a mole number. It is the number of molecules you would have in 18 milliliters of water. Why 18? Well, on the periodic table, you'll see that oxygen is 16 for its mass, and hydrogen is 1. And water is H2O, so there's 2 hydrogens. So that's 2 for hydrogen, 6 for oxygen. Add those together, it's 18. So that means that 18 milliliters of water will have 6.02 times 10 to the 23rd molecules. If you had a mole of marbles, you would cover the entire Earth. I can't read it. 60 miles deep? Yeah. It's a lot. It's a big number. If you had a mole of moles, then they put nose to tail would reach all the way to the Alpha Centauri, our nearest star. And they would weigh a third more than the weight of our moon. So a mole is a very, very big number. Now, because of all that, chemists are really into moles. And I'm a collector. And I have a variety of moles. So this is Professor Mole. This is Guacamole, and he's mute, a mute mole, because I can't do ventriloquism. And there's his wife, Minnie Mole. And a mole that a student made for me. I also have a mole fetish. Now, it's not the fetish you're used to hearing of. A fetish can be a statue of a god made by Native Americans, of their gods. And so I have a couple of those. Actually have become collector's items. And nowadays they're very expensive. Fortunately, I bought mine a long time ago. It's just little carvings made out of stone of the creatures. And in my case, I have one of the mole. And that was their god of the underground. So I like that. So every October 23rd, 10/23, from 6:02 a.m. to 6:02 p.m., I celebrate Mole Day. And when I had a classroom and did that, on Mole Day, my students had to bring mole food. So we'd have molios and lemonade, chicken mole, donut moles, just all sorts of mole food. And we'd share that with everybody. And then we would play mole trivia games in which you had to figure out. Now, the person who came up with the concept of the mole was Amadeus Avogadro. And so there'd be a lot of mole things based on his name and on other things. I think the worst one was probably what kind of cookies did Avogadro eat? And the answer was molasses. Disgusting thought. So the mole is an extremely important concept. I have to unplug it first. Now let's just leave it. In chemistry, and now I'm going to show you why. Concentration. There are different ways of showing concentration based on the units that you use. But concentration is how much solute is dissolved in a certain quantity of solution. So we have one term called molarity, and that's abbreviated with a capital M. A very widely used, the most commonly used one, of expressing concentrations. It's the number of moles of a solute in a liter of solution. So you simply take the volume in liters, or if you're harmful to yourself, cubic decimeters, you divide the number of moles by that. So for example, what would the molarity be of a 1.5 liter solution with 4.5 moles of sodium chloride? Anyone tell me what the answer to that would be? I know you don't have access to your electronic brains right now.
Would it be 3?
Excellent. 3 what?
3 molarity?
Yeah, or 3M. Correct.
Mhm.
That's right. Because all you do is take the 4.5 moles divided by the 1.5 liters. So you get 3 molarity. Another example, what's the molarity of a solution with 65 grams of calcium chloride and 150 grams of water? I'll take you through this. Now, this way of solving a problem is called multifactorial dimensional analysis, or just simply dimensional analysis. By a show of hands, how many of you have seen this method used for problem solving before, where you have a horizontal line and then straight lines and units? One here. Online, we have any hands?
Tiffany and Marielle.
Excellent. Yeah. Right, Christina had her hand up. So that's three of you, and the rest of you, if you take chemistry, you're going to come across this and we use it in chemistry, and some of the physics teachers use it. And personally, I think it's one of the best inventions ever, because it's a way of canceling units and making sure you're doing the problem right. There's never any doubt when you're done as to whether you set the problem up right, because the units cancel and they come out and give you the unit. And if it doesn't give you the right unit, then you didn't set it up right. You don't have to memorize things like, do I divide by this? Do I multiply by that? It shows when you do this. So with the problem, you have 150 grams of water, and it says you need to convert the grams to milliliters, which water is 1 milliliter per gram, or 1 gram per milliliter. It works both ways. And Carl, I need to, yeah. And then you need to convert your amount of water to get the into liters of water, and you simply multiply by everything on top, divide by everything on the bottom, and you end up with 0.15 liters of water. But that's not what the question asked for. It asked for the molarity. Well, now you know the volume of water, you can go to the next step. You've got to know what is the molar mass for calcium chloride. And to find that, you use the periodic table. We went over that once before. You look up the mass of calcium, you look up the mass for chlorine, multiply the chlorine by 2, because there's 2 of them, add that all together, and you get 110.98 grams per mole. That's the molar mass for calcium chloride. Then you use the 65 grams that was given in the problem and divide it by the molar mass. And you end up with 0.59 moles. But that's not the answer, because it asks you what's the molarity. And molarity is number of moles divided by the volume. And so we have the bottom line there, and our 0.59 moles divided by the 0.15 liters that we came up with before, that gives 3.9 molar. So a fairly complex problem, but when it's broken down into steps and you use dimensional analysis, it's really very easy to figure out. Molarity is the most commonly used method for concentration. Molality is also used less commonly. Molality, we abbreviate with a small m, lowercase. It's the number of moles of solute dissolved in a kilogram of solvent, not not solution, but solvent, just the solvent. And it's given in the equation, moles of solute divided by kilograms of solvent. And I'm not going to go through a problem, because it's done the same way as the others. So we're going to take a look at what that accomplishes. Freezing point depression. When you have the solute dissolved in a liquid solvent, the freezing point of your final solution is lower. How much lower? That's where you use the molality. The amount of freezing point of a solvent can be lowered. It's dependent on 2 things, and one is the concentration. That makes it a colligative property. It's not based on chemical reaction. Colligative means it only matters how many particles there are. Now, when sodium chloride dissociates in water, you get, for every 1 atom of sodium, you get 1 of chlorine, or ions actually. And when calcium chloride dissolves, for every 1 calcium, you get 2 chloride ions. So that means that calcium chloride is going to be more effective at lowering the freezing point of a liquid, because it has 3 particles compared to sodium chloride's 2 particles. Colligative properties are based strictly on the number of particles. Also, the nature of the solvent. 2 solutions of the same concentration with the same solute will freeze at different temperatures if they're made with different solvents. So those are the two things that affect freezing point depression. Is that important? Well, if you went for a drive recently when it was snowing outside, it would have been awfully nice if they'd have put some salt down on that ice, because it would make the ice melt, because it would have to be a lower temperature to freeze. And of course, some places get that low. Also, in your car, in the radiator, you have antifreeze. That's ethylene glycol. It's added to the water in the radiator, and it lowers the freezing point of the water so that when it gets below 0 degrees outside, your radiator doesn't burst. So this is the equation for determining that. Delta T sub F is the change in freezing point, how much of a change in the temperature. And K sub Fm is a proportionality constant. It's 1.86 degrees Celsius per mole for water. How do you know what it is for the substance you're working with? If you're in a research lab and you want to find out what this substance will do, there's a very thick book called the Handbook of Chemistry and Physics. And it has very pages with very small type, and it is just loaded with tons of information. And that's the sort of thing that you turn to that book and you look it up and you find out. Besides having freezing point depression, we also have boiling point elevation. Sorry, wrong way. The boiling point of a solution will increase through the addition of a solute to a solvent. That means it's also a colligative property. It's based on the number of particles, not what they are chemically, not how they react. You'll always read that when you go to make some spaghetti, you get your water boiling and you add salt to it and then put your noodles in. And people will tell you that that's because it'll raise the boiling point in order to cook the noodles faster. That's completely false, because there's not going to be enough salt to significantly affect the temperature, the boiling point for the water. The only reason to add that salt is if you want the flavor. And that's why I don't put salt in my water for spaghetti, because I'm trying to keep my salt intake a bit lower. The sum total of both of these, boiling point elevation, freezing point depression, is that when you add a solute to a liquid, it extends the liquid range. It keeps a liquid longer. And that's a very important thing. It's why water in the ocean, deep water, doesn't freeze. It's why even in lakes, the bottom doesn't freeze. So animals can still survive down there. Adding salt to ice on the road will melt the ice, as long as the temperature is not too low. And there's the boiling point elevation equation. That the change in temperature is based on the molality again. Now, I mentioned nature of solute and solvent before. The nature means the polarity of the substance, whether it's polar or nonpolar. And remember, the shape of a molecule determines its polarity. So if we have a symmetrical distribution of electrons, on the left there we have CH4, which is methane, a gas, and there's a symmetrical distribution of the electrons. And so that is nonpolar. Methane is a nonpolar compound. In the case of the one on the left, one of the hydrogens has been replaced by a fluoride ion. Fluoride, you may recall, is the most electronegative element. So it's going to pull the electrons towards it. And that means that that molecule is going to be much more negative on that side of the molecule. So that is a very polar molecule. So why does that matter? Because of this general rule of solubility. Like dissolves like. Polar compounds dissolve polar compounds. Nonpolar compounds dissolve nonpolar compounds. If they have the same nature, they'll dissolve. And if they don't, then they won't. Two polar substances would be soluble, they would mix. But a polar and a nonpolar will not. And here we see sodium chloride, that's an ionic compound. It'll dissociate into positive sodium ions and chloride ions. That's a very, very polar compound. Iodine, which is I2, the two atoms are the same, they have the same electron. There's no separation of charge at all there. And so that's a very nonpolar compound. And hydrogen fluoride, very, very strong separation due to the high electronegativity of fluorine. And so it's a highly polar compound. Solubilizers. We're nearing the end. So how can you get a nonpolar substance to dissolve in a polar substance? That's something you often want to do. And nonpolar will not dissolve in polar. So how can you get around that? You need something that's going to be attracted to both. It's going to be attracted to a polar compound, and it's going to be attracted to a nonpolar compound. How do you do that? You need a surfactant. Surfactants are compounds that lower surface tension between two liquids, or between a gas and a liquid, or between a liquid and a solid. The idea is that the surfactants act like detergents, wetting agents, emulsifiers, foaming agents, dispersants. The word surfactant is simply a blend of surface active agent. And that's what's shown up here on the right. We have different kinds of compounds with hydrophilic bonds. One end is polar for these, either negative or positive. And if it's polar, then that's going to dissolve in, say, water. The other end is a long chain of carbons, and that's going to be nonpolar. And so that will dissolve in a nonpolar substance. And actually, if you get a whole bunch of these, they will form a sphere with the lipid ends on the inside, the polar parts on the outside in water, because water is polar. And that is the idea of micelles, and that is the idea of how life is thought to have begun on Earth by the biologists. Nova had a special on a week ago in which they called The Origin of Life. They brought this up and then said no more about the origin of life because they didn't know. They said that's one of the greatest mysteries in science now. But we don't know how life starts, as far as science knows. Typically, a surfactant is an organic compound having a hydrophilic, hydro, water, philic, loving. So hydrophilic means it loves water. It's a polar compound. And a hydrophobic, which fears water, tail. And that's what this compound is. A really good example, and I talked about this last time a bit, SDS, sodium dodecyl sulfate. The IUPAC name, IUPAC stands for the International Union of Pure and Applied Chemistry, and they're the world authority on naming compounds. And so they said, oh, let's call this sodium lauryl sulfate. And that's fine, except everybody's been calling it SDS for many years, and it's very hard to get old fogies to change like me. So I'll just stick with SDS. And there's a diagram of the molecule showing that we have one end polar charged, and the other end is a hydrophobic tail. It's a synthetic organic compound. It's made, not naturally occurring. And that's its chemical formula. It's an organosulfate on one end, a salt on the other. Whoops. It's an anionic surfactant, meaning that it's going to give a negative charge. And it's used in a lot of cleaning and hygiene products. I mentioned last week that you'll find it in your toothpaste and an ingredient in a lot of the other cleaning materials in your house. And that's its molar mass. We'll be using SDS for our electrophoresis of our proteins. It will help to digest the tissues in order to get the polypeptides out. And it's also used in the running buffer during electrophoresis. Because it's surfactant, it's going to unfold the proteins. When it does that, then the amino acids are all exposed. Normally, the amino acids that are nonpolar end up being in the center when the protein folds up into its quaternary shape, or tertiary state, I mean. And this will expose all of those so that the SDS can react with them. And because SDS is anionic, it'll end up changing all the charges, and it's going to give a much greater charge than the amino acids give, and so it makes the whole molecule negative. And that's why the polypeptides, because of the SDS, will all go towards the positive pole during electrophoresis. Otherwise, you have some going positive and some going negative. It would be a major problem. But since it's negating the effect of charge, then that means the only thing that matters as to how far the polypeptides move is their size. We'll also be adding a compound called 2-mercaptoethanol. That destroys disulfide bonds. You might recall I said that those are very strong bonds. And so those have to be broken in order to get the polypeptides to unfold. And mercaptoethanol has a very interesting odor to it. And that's all.